Okay, kids, so a little bit jacked up. Howdy. We'll see how this is going to go. Kind of had to rig this whole thing because I can't lecture with my smartboard. So anyway, so we're going to try and give this a go. So there's already a video out on YouTube on introduction to circuits, and that kind of shows like a physical layout of some stuff and how they actually look. And I'm going to kind of go in between this platform here and then that circuit builder on that FET simulation. So hopefully I'm going to write big enough that you all can see this. This is just kind of an introduction to some of these equations. So if you're going to have a circuit, basically what you need is some type of source, usually like a battery or a power company, or maybe, I don't know, a set of solar panels, I'm not sure. And you have a battery, and then that electricity is going to do something. We'll have a light bulb, and then it's going to come back, and this is going to be the positive terminal, and this is going to be the negative terminal. Now, because of Ben Franklin, he had a 50-50 shot on current, whether it was the positive charges that were moving or the negative charges that were moving. He had a 50-50 shot. He chose the positive charges. So it's actually the electrons that are moving, but and don't sit there and argue and go, wow, why don't we just change it? Just accept it, okay? Just accept it. You just sit there, shake your head, and go, yes, Mr. Burkamp, it's okay. So we got this current going around. We're going to define that as being, go away. We're going to define that as being positive charges moving from the positive terminal around to the negative side. Now, in reality, it's the electrons that are moving. Don't get hung up on that. Literally, don't get hung up on it. Let it go. Just accept it that this is how we're going to define a current as positive charges moving. So here's a light bulb, emitting some light, okay? And so this current is going to come around, and the whole purpose of the battery is this equation. The delta U equals Q delta V. So the purpose of the battery is to give electrical potential energy to the in actuality, the electrons, we're going to talk about the protons. So remember, Q is your charge, which is going to be in coulombs. Your delta V, which is your voltage, which is joules per coulomb. So coulombs cancel out, you get joules. So the purpose of the battery is to give energy to the protons, that electrical potential energy. So it gains that energy, it comes in, it does something with the bulb, makes the bulb glow, and they come back here, and then they have no energy. So a lot of times what you'll see is that you'll see a battery being like an energy escalator. So the protons leave with this energy. It does something, it does light bulb, makes toast, something. They lose that energy, they come back, they're depleted of energy, they go up this energy escalator, they come back out, and they just repeat the cycle. So the whole purpose of this is to make these protons have energy so they can go out and do something. Now the other big equation that you're going to need is Q equals IT. So Q is your charge in coulombs. This is current, which is measures of amps, which is coulombs per second. And then you have time, which is in seconds. So basically all this is saying, okay, if I have a certain amperage, so let's say for example, your house might have like a 15 amp breaker. So on a 15 amp breaker, that means that you have 15 coulombs per second flowing through that circuit. Here's their time in seconds. This is the amount of coulombs and charge that's going to happen. So if you look at a simple little substitution, and you combine a couple of things, we said that delta U equals Q delta V. Well, we can also come in here and say, oh, if current equals IT, then by doing some simple substitution, you can go, oh, delta U equals IT delta V. You're going to end up with the same thing. So all this is showing is that the more current that you have flowing over a longer amount of time, with a greater energy per coulomb, the more energy that you're going to store. Okay, that's just the short version of it. Okay, so when you talk about voltage, sometimes you'll see voltage also referred to as EMF, and that stands for Electro-Motive Force. So if you see, and this is on your equation sheet kind of on the bottom right hand side, they use this more when we get into magnetic fields, but sometimes you'll see it written as this kind of a fancy E, okay? A fancy E means the same thing as electromotive force, which means the same thing as voltage, okay? Because it's talking about how much energy you are giving that as it flows through. So the other big equation, we'll talk more about this tomorrow, is Ver, okay? So V is your voltage, and you'll see this in just a second. Here's your current, coulombs per second. And R is your resistance. So resistance is basically, you know, how if you think about electrons moving through a hallway, your resistance is how difficult it is to make those particles move through the hallway. So the great analogy is if you look at this in terms of like a dam, okay? So here's this water. So you've got this dam up here, and you have the potential for this water to flow through. So the height of this is kind of like your voltage, okay? So there's two ways that you can make this water come down. You've got a really, really small straw, or you've got a really, really big pipe. So if they're at the same height, whether it's a straw or this big tube, they both have the same voltage, okay? So, but the little straw obviously can't get as much water coming down from the top down to the bottom, but that big concrete pipe could have a lot of voltage, or excuse me, a lot of current that goes through it. So, just because you have things with the same voltage doesn't mean that you're going to have the same current. The other thing that impacts that is resistance, which we'll see here in just a second. So, you've got this big equation, Ver, okay? Then what you're going to need for the assignment, and by the way, I'm going to scan that assignment, and I'm going to send that to you. So you're going to have delta U equals Q delta V, and then you're also going to have Q equals IT, okay? Those are the big equations that you're going to need to start off with. Now, the other thing that happens with current is something known as Kirchoff's rule. So that's easier shown on an app. So if I go to this FET simulation, and so what I've got here is that I've got a battery, and the voltage across the battery is 9 volts, okay? So that tells you how much energy is being gained as this goes through. Now, this is showing the actual movement of the electrons this is going through. So if I change that to like the conventional idea, thank you, Ben Franklin, then you'll notice that the current is showing going from the positive terminal around to the negative terminal and going around like this. So when we talk about current, especially once we get into magnetic fields, this is how we're going to define current. And your thumb is always going to point in the direction of the current. We'll talk more about that later. So down here, I've got an ammeter. Now, when you watch the video, most of the time amp meters are actually like hooked up and it's part of the circuit. So this is cool because it's what's called a non-contact ammeter. So what I want you to show here is that I've got a current right now of 1.80 amps. I've got a voltage of 9 volts. And so what I could do is I could calculate the resistance of that bulb, which we'll get into later, because I know my voltage, I know my current. We'll get into that later. I'm just telling you, that's how you could use your resistance. So if I come over here and I move these terminals to here and measure the voltage drop across the battery, that's 9 volts. So I've got this terminal coming around like this, so this is where this energy is going, is into that bulb. Now, don't confuse energy with current, and this is going to be the next big thing. So if I move this amp meter anywhere along here, okay, notice that my amps stay at 1.80 amps. So don't think this like, oh, well, that I won't have as much current after it comes through because it's losing that energy. So don't confuse energy with current. That current is going to be the same all the way through now. This is just a simple circuit. Everything is hooked up in series, okay? It's all coming around like this. But to make this a little bit more complicated, I'm going to close this, and now I've got two parallel circuits. So I've still got this one, but now with this resistor down here, now I have this current flowing in two different directions. But here's what you need to get out of this. So if I move this amp meter up here, notice that that's 2.70 amps, okay? If I move it over here, it's 2.70 amps. So anywhere up here, even over here, it's 2.70 amps. But if I move that amp meter to here, I'm at 1.8. So I have 1.8 amps coming down here, and then if I move it down here, that's 0.9 amps. So if you do a little bit of math, this current up here was 2.70. This becomes down here 0.9, and that's 1.8. So if I take 0.9, which is that lower one, and 1.8 and add that, that adds up to the 2.70, which is the total current in the circuit. So this is what's known as Kirchoff's rule. So if you ever read like an introduction unit, read the beginnings of chapter 22, about the first 3 units, because it kind of gives more of the theory about what's happening. It goes through the electric fields and all of that. So you don't have to, but I'm sure you all have plenty of time. So what I would recommend is if you go through and try and read the beginnings of those units. So here's what you have to get out of today. The current, okay, that you're going to have is the sum total of these branches is going to add up to what you begin with. So think of it as like a river. So I've got 2.7 flowing here. It breaks up into 1.8 and then 0.9, so that adds up together. But then when they rejoin over here, then I get back to 2.7. So this is my current. So if I know how long this thing is flowing, so if I know my time, I can figure out the amount of charge that's going to flow through it. So if this is a 2.7 amps, so that's 2.7 coulombs per second. So if I multiply that by 10 seconds, that's how long I let this thing run, that means that I would have 27 coulombs that circulated through that. Now, if you want to find the number of electrons, remember electrons or protons have the same charge, 1.9 times 10 to the negative, or 1.7 times 10 to the negative 19th coulombs. So you can figure out exactly how many electrons or protons are circulating through that current. So this first assignment is pretty easy. I've got that scanned. I will send that to you. If you want to begin to play with this PhET simulation, you can. And if you want to prove that Kirchoff's rule, you've got that as an option. So here's what you need to do. Obviously, watch this, because if you're seeing this, you have watched it. And then also there's the other one on the introduction to circuits, which actually shows the physical layouts of them. And then I'll send you the scanned assignment for assignment 22-1. So good luck. We're all counting on you. See you tomorrow.